This is the key for the Unit 12 practice exam. So I'll start here with Section A, which is multiple choice concepts. Just reading through here, it says, which of the following describes a substance in liquid phase? In a liquid phase, we're going to have variable shape and definite volume. What this means is the shape changes, but the volume stays the same, meaning if you dump a liquid from one container into another, the volume will stay the same, how much liquid we have, how many milliliters, for instance. But the shape is going to change depending on what container it's in. Definite shape, variable volume isn't anything. That doesn't even make any sense. Definite shape, definite volume, B there is what a solid would be. This is C. It says, of the different states of matter at room temperature, solids have the blank attraction between particles. If they're solids at room temperature, that means that there's going to be a strong attraction. It keeps those particles really close together. So 2 is A. Generally speaking, in gases, the particles are really spread out. That's just kind of a general idea of gases. Solids, they're really close together. Liquids, a little bit more spread out, just to the point where they can kind of move around past one another. And then in gases, they're completely spread out. Number 4, the attractive forces within molecules, which are also called the bonds. These are called intramolecular forces. So intramolecular forces are the bonds. When a liquid is converted, it is converted to a gas at a temperature below the boiling point, it's called. So on this one here, the phase change that we're talking about here is going from a liquid to a gas. And it says it's below the boiling point, meaning below the temperature at which it would normally boil. And so this is a special phenomenon which is called evaporation. It's when just a little bit of gas escapes the surface of a liquid below the boiling point. If it's at the boiling point, it's called vaporization. But you would see boiling and bubbling if that were the case. Question 6, how does increasing the atmospheric pressure affect the boiling temperature? If we increase the atmospheric pressure, that means there's more bombardment of particles coming from the air, making it hard to boil, which means the temperature is going to go up. Number 7 is the heat. The heat that is absorbed as a substance melts is called. Okay, so if it's melting, we don't actually have a heat of melting, so B is a decoy answer. It's called heat of fusion. There's also, this would also be called heat of fusion if we were talking about something freezing, so that is that. How does heat of vaporization compare to heat of fusion? Generally speaking, heat of vaporization is always going to be higher than heat of fusion. The reason for this is because for vaporization, the particles have to get really, really far apart, versus fusion is just spreading out a little bit so it can move around as a liquid. Number 9, which of the following processes is endothermic? If you look at these, the only one where you'd have to put energy in is sublimation, which is going from a from a solid to a gas. Deposition is going from a gas to a solid. Freezing is going from a liquid to a solid, and condensing is going from a gas to a liquid. So make sure you know all of those. There's a little chart in your notes that you should look at. So this is a 10 here. It says 2 substances exist at the same temperature. One is a solid, one's a liquid. Which substance has the higher average kinetic energy of its particles? Okay, the key word here is, or keywords is same temperature. If they're the same temperature, that literally means that they have the same average kinetic energy. That's the definition of temperature, is average kinetic energy. So that's C. When a substance deposes, so this is talking about deposition, what effect does it have on the kinetic energy of the particles? Deposition is a change of state. A change of state only affects the potential energy, not the kinetic energy. So Ke is going to stay the same here. And then question number 12 is asking about the potential energy. So if we're deposing, we're going from a gas down to a solid, and that means that we are losing energy So PE is going to be decreasing. All right, now on to the back here. So this first question is about phase change. So you know for that one, you're either going to be using the heat of vaporization or the heat of fusion. In this case, it says helium gas is converted into liquid. So we're going to be using heat of vaporization because vaporization is used whenever we're going between a liquid and a gas or vice versa. And heat of fusion is when we're going between a solid and a liquid or vice versa. So on this one, we say delta H equals m times heat of vaporization. The way that this looks when we're doing it in just one step normally is we've got 14.00 grams of helium gas. For every 1 gram of helium that we have to look here, heat of vaporization of helium, it's 19.99 for heat of vaporization joules. We multiply those together. 4 sig figs and 14.00, 4 sig figs and 19.99. As a note, this 19.99 is going to be negative because it's going from a gas to a liquid, which is an exothermic process. So you multiply them together, we end up with negative 279.9 joules. All right, so then we look down here in our list. We find that that is answer D. That's that. Going down here to number 14, this is a heating curves problem. It asks how much energy is needed to raise 175 grams of ice at 0 degrees Celsius to water vapor at 100 degrees Celsius. So we're starting here, ice at 0 degrees Celsius. It has to be on the left side of the line because that's the solid side. The right side of that line is the liquid side. So the first step here then is we have to melt the ice, get it to be from a solid to a liquid, and then we have to heat that liquid up, and then we have to boil that liquid, and then it is a gas at 100 degrees, which is where we're stopping. So there's 3 steps. The first step, melting, so delta H equals mass times heat of fusion, which equals 175 times 334. Multiply those together, and we get 58,450 joules. Next step, heating the water up from 0 to 100 degrees Celsius. So since we're heating it up, it's Q equals MC delta T, which equals 175. C for liquid water is 4.184. Change in temperature here, 0 to 100, so that's 100. Multiplying those together, I get 73,220 joules. 3. Okay, this is the step where we're boiling it, so we know delta H is going to equal mass times heat of vaporization, which equals 175 times, if you look up there, the heat of vaporization. By the way, I should actually take a moment to say up here, right next to this table on the right-hand side, you see that I give you the specific heats and the heat of fusion and the heat of vaporization. And so all that information is provided. You don't have to memorize any of that. So when I'm pulling those numbers, it's from there. 175 times 2256. Multiply those together. I get 394,800. And then I add all of those up, and I get 526,470 joules, which is B. On to number 15. This is also a heating curves problem. This one, it says, starts at 80 degrees Celsius, it cools, then we freeze it, then it goes down to negative 20. So that's 3 steps there. I add little arrows in here to show that it's going in the negative direction, going down the curve. Step number 1, we've got water cooling from 80 degrees down to 0 degrees. So step 1, we've got Q equals mc delta T, which equals 25.0 times 4.184 because it's liquid water, times the change in temperature, which is negative 80 degrees because it's going down by 80 degrees. Multiply all those together, we get negative 8,368 joules. Next step, we're going to freeze the water. So on this one, delta H equals mass times heat of fusion, which equals 25.0 times 334. And this is going to be negative in this case because we're freezing it, which is the exothermic process. Freezing is exothermic, melting is endothermic. So this one is negative 334. We'll find what that's equal to. We find that it's equal to negative 8,350 joules. Step 3. Last step here, we're cooling the ice down from 0 down to negative 20. So this is a Q equals mc delta T again, which equals 25.0 times C 2.060 for solid water, and then delta T negative 20. Multiplying those together, I get negative 1,030 joules, and then if we add all of those up, I get my total Q equals negative 17,748 joules. If I look here at the list of answers, I find the positive value of that, but I don't find it as a negative value. So because this one is exothermic, it's going to be E, none of these. As a note with these heating curve problems, either all of the steps are going to have positive values like in problem 14, or all of them are going to have negative values like problem 15. You're not going to have them intermixed where some are positive and some are negative. All right, lastly here I have one of the throwback questions for this unit. What we have here, it's a density problem. In order to do these problems, you need to have memorized this little algebra circle which says density is mass over volume. And this actually gives you 3 different equations that you can use. You just cover up the variable that you want to solve for. So if you covered up mass, you get that mass is equal to density times volume. If you cover up volume, you get volume equals mass over density. So in this case, it says, what's the density of osmium? So we're finding density. Density equals mass over volume, which equals the mass here in grams, 455,190 grams divided by 2,000 centimeters cubed. So I won't include the units there. Actually, I probably had better, grams per centimeter cubed, so that you can see it at the answer here. So we're taking grams divided by centimeters cubed. The answer that we get here is 22.60 grams per centimeter cubed. Grams per centimeter cubed. I'll have you note here that this had 4 sig figs. It had 4 sig figs because the top number, our mass, had 4 sig figs, and the bottom number, 2,000 point, had 4 sig figs. So we rounded our answer here to 4 sig figs as well. So as a recap, we have sig figs on the throwback. This was A. We do not have sig figs on any of the heating curve problems. We do care about sig figs here on this first one, though, so we rounded that one to 4 sig figs as well. So careful about that. Make sure you know which problems have sig figs and which ones don't. And I think things should be pretty good. All right, that is that.